Whenever I upload a video about my Mario 64 optimization project, I get asked about implementing the famous fast inverse square root function made famous by Quake 3. This algorithm computes 1 divided by the square root of x only with simple operations by exploiting neat properties of how the computer represents floating point values. This allows you to skip computing a square root directly, which is usually very expensive. And old computers often had to run much more expensive approximation algorithms like this one here. I will explain to you why most of the time this is a bad idea. But I will also show you when it is a good idea, and I will even show you a little improvement over the algorithm listed on Wikipedia that works faster and is more accurate for most use cases. As well as a completely new spin on this algorithm that might come in handy. The problem with using the fast inverse square root algorithm is not that it is a bad algorithm, but rather that most of the time on the N64 we have a much better option available to us. The N64 has special hardware parts that let it compute the square root in a single instruction that takes 29 cycles. This is the exact same cost that doing a divide instruction costs. So if we compute 1 divided by the fast inverse square root of x instead of the square root of x, we really just tack the cost and accuracy loss of this function on top, which is all around terrible. Here is a table comparing the cycle costs for using the built-in square root function and using the fast inverse square root with 0, 1 Newton iterations. Don't worry about what a Newton iteration is just yet. It's just a cheap little thing we can do to increase accuracy. For this reason, it only ever makes sense to use the fast inverse square root function if we actually want to compute 1 divided by the square root of x, and never if we need the actual square root of x. Additionally, there is another issue. We are not CPU bound on the N64 at all. The N64 is possibly the machine with the worst memory to CPU speed ratio of all time. To render at 30 FPS, we need to finish a frame in 33,000 microseconds. In this scene, you can see that the CPU doesn't even use half of that time, while the renderer needs all the time it can get. The renderer and the CPU share the same memory, so any optimization we make should aim to improve memory throughput to make the RAM bus go vroom vroom. While using the square root and divide instruction to get 1 divided by the square root of x takes 58 whole cycles, it also only takes 2 instructions. Loading 8 instructions takes 60 CPU cycles, and it stalls the rendering for a bit, which is a whole lot worse than just running the CPU a little slower. Here is a comparison for computing 1 divided by the square root of x. If you look at the graph, you can see that the instruction count for the fast inverse square root is higher regardless of how inaccurate we go. This is because, while the fast inverse square root uses a bunch of quick to run instructions that just move numbers around in memory, it has to use a lot more than just divide and a square root instruction. There is one saving grace here, and that is cached code. The cache is like a memory that the CPU can use all by itself very quickly without disturbing the renderer. It can hold 16 kilobytes of information, and it's our best friend as far as optimizations go. If our code is already cached, we don't have to pay any cost per instruction beyond the first caching, making this negligible. I've rewritten Mario 64's graph render engine to fit all into one block of code cache, meaning if we use this somewhere in engine, we can avoid this cost and make this whole column irrelevant. But even then, there's another issue with the fast inverse square root function. The accuracy is reduced. We can't use this for any type of code that values the accuracy more than the tiny performance benefit that this offers. In this video, I've used the fast inverse square root to normalize the view matrix. And while you might not be able to see the accuracy loss right away, I think the accuracy loss is more noticeable than the 0.5 microsecond CPU gain that this algorithm offers per use. All of this means it's looking very grim for the fast inverse square root function ever being useful. With all these factors working against us, is there ever a situation where it's faster? Yes, actually. We just need to fulfill all 3 of these conditions. 1. We want the actual inverse of the square root and not the square root itself. 2. The code we are running is already residing in instruction cache. 3. We don't need very high accuracy. This leaves only a single use case that I can think of right now. normalizing vectors for unimportant graphical effects, which is coincidentally the exact same use case Doom had to make this algorithm as famous as it is. Normalizing vectors works by multiplying with 1 divided by the size of the vector, and the size of the vector is the square root of all the elements added together. Meaning we can substitute 1 divided by the square root of x with the fast inverse square root function here, and our first condition is passed. I managed to compress the code for the graph render into just 12 kilobytes, which is less than the 16 kilobytes of instruction cache that we have, so our second condition is passed as well. And additionally, it is not important that the vector is perfectly normalized for unimportant effects like shadows, so we passed all 3 conditions. Additionally, we have a little advantage here. Because the inverse square root function has inaccuracies, we don't have to worry about dividing by 0 in this spot anymore, and end up saving an additional 3 cycles for a total of 58 cycles saved. This is another small advantage for the fast inverse square root algorithm, and it ends up making it just a tiny bit more valuable. I went with the lowest accuracy version of the fast inverse square root, which saved around 80 microseconds per frame on the CPU, which means data is fed into the GPU more efficiently, where it saved around 20 microseconds per frame, which is a much bigger improvement than I initially expected from investigating this. And the inaccuracy is at most around 3%, which is the difference between these 2 circles. Of course, the average difference is much lower, and I doubt anyone would actually notice the inaccuracy in gameplay. But the fast inverse square root algorithm as shown on Wikipedia was just a 35-year-old algorithm that wasn't fully cooked back then. Let's see if we can improve on it. There are a few obvious accuracy improvements to this, like optimizing all 3 constants instead of just this one here. And there are a lot of scientific papers on a subject already that we could simply copy-paste. If you've been counting cycles throughout this video, you might have thought that I was off by 1 on all the Newton iterations. But that's actually because there's 1 cycle improvement you can make over the algorithm listed on Wikipedia. You can actually just bit tag even harder and subtract 1 from the exponent instead of multiplying by 0.5 in a normal inverse square root algorithm. This saves 1 cycle on the N64, and I've been comparing with this algorithm the whole time throughout the video. It only works if your number is bigger than this tiny number shown on screen that I'm not gonna pronounce, but like, come on, your number won't be that small. I can't imagine I'm the first to think of this, but I figured I'd mention it before you guys cook me in the comments. But since we actually use the simplest and least accurate version, we only want to optimize the version of this algorithm with no Newton iterations, which somehow doesn't seem to have any research done on it, so we can get to be the first to optimize it. Optimizing this is surprisingly very simple, because all I had to do for it is write a brute forcer and let it run on my Nintendo 64 overnight. Since all our vector norms are going to be in the range 0.03 to 1, we can simply iterate over all floats in this range and try all the constants and then use whichever one ended up having the lowest maximum relative error. Running the brute forcer directly on the same hardware that this algorithm will run on also accommodates for all kinds of hardware quirks that we might not know of. After letting my N64 run overnight, the best constant it found was 0x5F378171, which is not far off what Doom used at all and improved accuracy by just 1.9%. One other idea that Silaslock had was to not compute the fast inverse square root, but instead compute 2 separate approximations for the 4th inverse square root using 2 different magic constants picked to cancel each other's error out, and then to multiply them together to get the inverse square root. What a cool idea. This gives us a 33% reduced error over the fast inverse square root algorithm, but it does cost 9 cycles more. To give you a comparison, the first Newton iteration cost 24 cycles, and it has a 90% increased accuracy. I think all 3 of these approaches are valid, and this new idea provides a pretty nice intermediate step. I'm sure there are some cases where each of these 3 functions is your best choice, and I bet at least one programmer watching this just went, yo, because that 33% accuracy gain was all they needed. But this concludes my research on this topic. I hope you learned something, and I'll see you in the next video. Bye bye.